Hola, mi clase. We are doing 9-3 where we're going to rewrite radical expressions. So a radical is a square root symbol. So it's another word for square root. It kind of talks about all of them, but this one specifically, we're just going to talk about square rooting. Since we're talking about quadratics, right, the opposite would be to square root something. So that's why this is coming into play right now. So a radical expression is any expression that has a radical symbol in it. So if it has a radical at all, 1, 2, 3, it's considered a radical expression. The radicand is the number or expression written under a root symbol. Okay, so you've heard of like dividend, things like that. So it's kind of similar to that. The dividend is the number that has been divided, or is the the divisor. So the radicand is the number that's being rooted, right? So it's the thing that's being rooted, whatever's under the square root or the root symbol. So then we have the product property of square roots. So what it says is if I have a radicand, I'm going to use our vocabulary, of a times b, so it's the square root of a times b, and my radicand is ab, I can separate it into two separate square roots. So I can do square root of a times the square root of b. So I can separate them and not leave them as a times b. I can do them as almost like two separate problems. And we're going to use this a lot today, okay? So it says, what is an equivalent expression for the square root of 63? So my radicand is 63, and what I want to do is use my product of square roots property that you just saw to simplify it and make it an equivalent form, but not have just the square root of 63. So what we do is we look at factors of 63. So what, 9 times 7, right? So I can then rewrite it as the square root of 9 times 7. Now I'm going to use that product property. I'm going to take square root of 9 and separate it to the square root of 7. And the reason I'm doing this is because the square root of 9 is perfectly 3, and we go times the square root of 7. The square root of 7 cannot be square rooted. It is not perfect. And so we would just say 3 square roots of 7. And this expression is equivalent to that expression. If I took in my calculator the square root of 63, I would get exactly the same answer if I took the square root of 7 and times it by 3. Okay, so these are equivalent expressions by using perfect squares and my product of square root property. All right, so it says rewrite each expression to remove perfect square factors other than 1 in the radicand. So remember, this is my radicand, 44, and we're going to square root 44, and we're going to remove any perfect squares. Okay, so 44 is the same as 4 times 11. I'm going to take the square root of 4 times the square root of 11, and I get 2 square roots of 11. That's because the square root of 4 is perfectly 2. Square root of 11 cannot be rooted. It's a horrible decimal, and so I just go 2 square roots of 11. This is the same as 2 times the square root of 11, but we just remove the timesing symbol. Kind of like when we do 2 times x is the same as 2x. It's the same idea. We remove that multiplication symbol. All right, so we have 3 times, right? This is the same as 3 times the square root of 27. So I'm using this same thing I was just talking about. So I'm going to break up 27. It's 3 times the square root of 9 times 3. 3 times the square root of 9 times the square root of 3. Notice this 3 just keeps coming down. I get 3 times 3 times the square root of 3. I can then put these together and I get 9 square roots of 3. And this is my equivalent expression, removed my perfect squares. So this says, how can you compare the square root of 20 and the square root of 2 times 5? Square roots of 5. So let's first break up 20. So square root of 20 is the square root of 4 times 5. And then that'd be the square root of 4 times the square root of 5. and the square root of 4 is 2 square roots of 5. So what we would do to work backwards, though, I'm going to show you the other way to do it. So when we got here, it's because we square rooted 4. So when we take 2 square roots of 5, if I want to get 2 back into a square root, in a sense, I have to square it. And so I'd go square root of 4 times the square root of 5. I'd use the backwards version of this product property and go 4 times 5 in 1 square root, and I get the square root of 20. So what I would say is to compare the square root of 20 and 2 square roots of 5 is I would say the square root of 20 is equivalent or equal to 2 square roots of 5. All right, so 36, we have the square root of 6 times 6. Well, the square root of 6 times 6 would just get me, oh, not 6, square root. It would just get me 6 because, here, I'll show you. Well, it's hard to explain. How do I put this? Well, we know the square root of 36 is a perfect square. It's 6 times 6. Since I have 2 matching ones here, when I square root it, I just pop out the 1. There we go. That's how I'm going to try to explain that. So since this right here is a perfect square, I have matching perfects. When I square root this, it gives me just the 1 because the square root of 6 times 6 is 6. Another way to look at it is if I go the square root of 6 squared, we know that the square root and squaring cancel each other out, and so that's how we get 6. Okay? Now if I do this, remember how I worked backwards? So 3 times the square root of 6 is the same as square root of 9 times the square root of 6. That's because this is 3 squared, right, times the square root of 6. That's the same thing. So then I would do 9 square root times 6 like this. And when I take the square root, 9 times 6 is 54. And so how do we compare them? Well, the square root of 36 is not equal to 3 square roots of 6. It's just seeing if they're equivalent, if they can be simplified to the same thing. And so that's just how we're going to compare them. If they're equivalent, great. If they're not equivalent, that's fine too. All right, I'm actually going to leave B blank, and I'd like you guys to see if you can get the final answer, is if they're equal or not equal to. Okay, I want you to practice it and see if you can do it. Okay, it says what is an equivalent expression for 6 square roots of 63 times 6 to the 9th? So now we have an expression as our radicand. We had been dealing with just a number. Now we have an expression. So we have to break up all of this to see what we can pull out as perfect squares. So the square root, I made it really big because I'm going to break up 63 and I'm going to break up x to the 9th. So 63 is 9 times 7. Now, x to the 9th, I want to break this up into perfect squares as well. And that means I'm going to break up x to the 9th into different pieces of x's. So I can do x to the 4th times x to the 4th, because that's 4, 5, 6, 7, 8 of them. And then I'm going to go times x. And when I do that, I have all 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We can technically put a 1 here. And so I did the same thing I did to 63, is that I just broke it up into 3 pieces instead of just 2. Okay, so then what we're going to do is we're going to take the square root of 9 separate from the square root of 7. And then I'm going to take the square root of x to the 4th times x to the 4th. And I'm going to explain why I kept those together here in a second. And then I'm going to go times x by itself. So the reason I did this is because this is actually a perfect square. X to the 4th times x to the 4th is a perfect square. It's similar to this. The square root of 9 is 3 times 3. See how it's the same exact thing? So another way we can write this is x square root of 3 squared. Remember how I did that on the last problem? So all of these are equivalent And so you can see how it compares to this. I could rewrite this piece as x to the fourth to the second. Remember how we did this when we did exponent properties? This is a power raised to a power. That's what this is. X to the fourth times x to the fourth is the same as x to the fourth raised to the second power. So now it's squared. So just like here, squaring and square rooting cancel each other out, and I get 3, because the square root of 9 is 3, times the square root of 7. When I do this, the square root cancels this squared out, and I get x to the fourth. And then I'm going to go times the square root of x, because that one doesn't have anything to clear out. So now what I'm going to do is I'm going to put kind of like my like terms together. So I'm going to put x to the fourth times 3, and I'm going to get 3x to the fourth times the square root of 7 times the square root of x. But because these are both square rooted, I can use the backwards version of this and put them in one radical. So 3x to the fourth, not times, because we're going to get rid of that multiplication now, square roots 7x. So anything that can't be cleared out of your radical just gets put back in the radical. Since square root of 9 reduces to, or simplifies to, I don't want to use the word reduces to, simplifies to the same as 3, I can pull that out. And since x to the 9th gets me x to the 4th squared, I can pull, and that gets simplified to x to the 4th. And since they're not in radicals, they get put together, and then the things that are in radicals get put together back in the radical. So this is our final answer right here. And it is equivalent to this. All right, we're going to do it again. So the square root of 25 is 5 times 5. And then I'm going to break up x to the third. So I'm going to get x squared times x. Okay? So then I'm going to pull apart my numbers. Remember, 5 times 5 is the same as 5 squared, just so we can kind of see that. And then I'm going to go square root of x squared. And then I'm going to go square root of x. Pull it out because it can't be simplified. So remember, square rooting and squaring cancel each other out. I just get 5. Squaring and square rooting cancel each other out. I just get x. I just get x, right? We just get the number, the base. These cancel each other out. And then times the square root of x. Since this cannot be cleaned up and these can get put together, I get 5x square roots of x. So this is the equivalent radical to my initial one. So it says, how can you write an expression for the product of these two radicals? 3 square roots of 5x times 2 square roots of 15x to the third, without any perfect square factors in the radicand. Okay, so now we need to combine everything we've just done to clean these up. So because 5x and 15x to the third are inside the radicals, they can get put together. And since 3 and 2 are outside of the radicals, they can go put together. So I'm using commutative property multiplication. So here, I'll show you. So I'm going to go 3 times the square root of 5x times 2 times the square root of 15x to the third. I'm going to use the commutative property and multiplication. 3 times 2 times the square root of 5x times the square root of 15x to the third. Now, we can just multiply these together. I get 6 times, I'm going to use my product of square roots property in a sense backwards and put these into one radical, 5x times 15x to the third. So I'm going to leave the 6 on the outside, and then I'm going to go times the square root. I'm going to use actually the product, the commutative property of multiplication again, and I'm going to go 5 times 15, put the coefficients together, times x to the third, and put my variables together. So 6 times the square root of 15 times 5, I believe is 75. Yeah, is 75. And then this actually becomes x to the 4th. So I'm going to now break them apart. I'm going to go 6 times the square root of 75 times the square root of x squared times x squared, because that's x to the 4th, right? 1, 2, 3, 4. I need to break up 75 into perfect squares. So it's going to be 6 times the square root of 25 times 3. And then I'm going to rewrite this as x to the 2nd squared. 6 times break up 25 and 3. I'm going to leave this for right now because I haven't cleaned up all my square roots yet. Getting close, getting close. All right, I'm going to come over here. Follow my little arrow. We're going to come over here. 6, so now we have 6 times 5, because the square root of 25 is 5, times the square root of 3, times, now remember squaring and square rooting cancel. I'm left with my base x squared. 6 times 5 is 30, commutative property multiplication, x squared times the square root of 3. And then to fully clean it up and be done, we just say 30x squared square roots of 3. And there it is. Now, I know this was a lot of work. As you get better at this, you'll be able to break these up sooner. I'm just doing very, very explained step by step so you can see exactly what we're doing. Okay? As you get better, you'll be able to break things up quicker and you won't need as many steps. But I'm just trying to show you so that you can see every step and understand exactly where every piece is coming from. Okay? All right, so it says write an expression for each product without perfect square factors in the radicand, and here it is. So let's do this. I want you to pause, and I want you to try this, but I promise I will explain it after the fact. So I need you to pause and try to see if you can break these things up yourself at this point and see if you can get to the same answer that I did, okay? And I might do it a little differently this time too. All right, so I've got 2 square roots. Well, I know that 4 times 3 gets me 12, so I can actually break that up right away. We've already broken up x to the 9th. I know that's x to the 4th times x to the 4th times 1. Or not times 1, times x to the 1st. I don't know why I wrote 1. Hold on. X, there we go. Then I can break up the 18. Well, 18 is 9 times 2. And then I can break up x to the 5th. What would that be? X to the 2nd times x to the 2nd times x. Is that 5 of them? 1, 2, 3, 4, 5. Yep. So then 2 times the square root of 4 times the square root of 3 times the square root of x to the 4th. I'm going to write it as squared. You guys have seen me do that. Times the square root of x times the square root of 9 times the square root of 2 times the square root of x squared squared times the square root of x. So 2 times 2 times the square root of 3 times x to the 4th times the square root of x times 3 times the square root of 2 times the square root, oh, not the square root, times x to the 2nd times the square root of x. So all I did is I went through and cleaned up all the radicals I could. The ones that couldn't be cleaned up got left. So 2 times 2 is 4. I'm going to move my x over, so times x to the 4th. I'm going to actually now move my 3 over because I didn't move it over yet. And then I'm going to move my x squared over. That way all my radicals are together. 4 times 3 is 12. X to the 4th and x to the 2nd would give me x to the 6th. Oh, look at this. I can put these together. So I'm going to go like this. Square roots of x times the square root of 3. Well, x times x is 12x to the 6th times the square root of x squared times the square root of 3. That gets me 12x to the 6th times x to the 3rd. And so now I combine these, and my final equivalence is 12x to the 7th times, oops, not times because I get rid of that at the end, square roots of 3. This is the equivalence. So you can see it really is still the same amount of steps in a sense, but I just, it's still a lot of work, but I did a lot of them in one. So back here in this last example, I did a lot of moving first and got them together, and then I started breaking them up. In this one, I actually broke them up first and then cleaned them up, moved them around, cleaned them up. So I just kind of did it in a different order. So it's up to you on how you want to do it. It's also up to you on how your brain works, on which order you want to do it in. But this is our final answer. Things to remember: that the square root is inverse of squaring. That's the main thing to remember. So that's why when we had x to the 4th squared and I could square root it, I get x to the 4th. I get that base, okay? So that's the main thing I want you to remember. So that's it, all done. You only have that one problem that you need to do yourself. I can't wait for all your questions. All right, adios until next time.